So now we're going to use the properties of exponents to rewrite some of our radicals. So the property of exponent that we want to look at first is the one that says if you have a root of a radical that contains a product, so that means whatever is happening between A and B, whatever those terms are, it needs to be multiplication. No adding or subtracting, only multiplication. And later on we'll look at what happens with division too. But for right now, only with multiplication. Okay, if you have a radical of two terms being multiplied, you can split it up into two separate radicals. So that's what we're going to look at here. I have the fourth root of 81 times a to the 8th times b to the 5th. So I can split that up into the fourth root of 81 times the fourth root of a to the 8th times the fourth root of b to the 5th. And then I'll evaluate each one individually and then put them all back together as I can. So the fourth root of 81 is 3. The fourth root of a to the 8th, you'll divide 8 by 4. And 8 by 4, 8 divided by 4 is 2, so a squared. Because a squared times itself 4 times is going to be a to the 8th. And then I'll divide 5 divided by 4. Well, 5 divided by 4 is equal to 1, and we're going to work with remainders this time. 1 with a remainder of 1. So I'll have b to the first power, and that remaining b, that remaining 1 over here, is the exponent on what's on the inside. B to the first power again, and that's the fourth root. So 3a squared b times the fourth root of b. So let's do an extra example. You can just add this one in. We'll do the fourth root of 1024, x to the 9th, y to the 12th. So I'm going to simplify. I'm going to write this out. The fourth root 1024 times the fourth root of x to the 9th times the fourth root of y to the 12th. Now, 1024 is not a perfect fourth power. That fourth root is going to be a decimal, but we don't want to write decimals. We want to leave our answers in exact form, which means we need a radical. So we're going to use the same idea you did before whenever you had to simplify something like the square root of 200. Since I was taking the square root, I was looking for a perfect square. Square root, perfect square. See what that has in common there? A perfect square that would divide into 200. Then you would take the square root of 100 and leave the 2 on the inside. We're going to do something similar, except instead of looking for perfect squares, I'm going to look for a perfect fourth power that will divide evenly into 1024. So this is, again, where that power chart becomes really convenient. And I've got one. I just have to scroll to it. Scroll. There it is. So here's my perfect fourth powers. And it ends up that 256 divides evenly into 1024. So then I can write this as the fourth root of 256 times 4. Then I can divide 9 divided by 4 is 2, so x squared with a remainder of 1, so times the fourth root of x. And then 12 divided by 4 is 3, so y cubed. So let's see, then the fourth root of 256 is 4 times the fourth root of 4. Then I'll bring down x squared, fourth root of x. Bring down the y cubed. And then I'll write my answer with one large radical. I'm going to combine everything back together. Make sure it's the fourth root. A 4 and an x are the only things inside. And on the outside, I've got this 4, an x squared, and a y cubed. So now let's look at the quotient property. The quotient property deals with whenever you have a radical of a fraction, you can split that radical up into two separate ones, one at the top, one at the bottom. So let's see how that applies here on part B. My advice on these, again, is to always try to simplify the inside. So I look on the inside and I see I notice an x to the fourth and an x to the first power. So I'm going to simplify what's happening on the inside first. So now if I do that, I'll have the cubed root. Since I'm dividing x to the fourth by x to the first, you can subtract those exponents because they have the same base. So 4 minus 1 is 3. So x cubed, y squared, and then 125 in the denominator. So now if I apply that property, I can split this up into the cubed root of x cubed. These two are being multiplied, so I can also break it up into the cubed root of y squared over the cubed root of 125. Well, 3 divided by 3 is 1, so x to the first power. 2 divided by 3 is 2/3. That's not greater than 1, so I'm going to leave it as the cubed root of y squared. And then really with that x to the first, we don't really write x, the 1 as the exponent. It's usually understood, so you don't have to write it. And then the cubed root of 125 is 5. So as you're working through these, you might start to think, how do I know if I've simplified it all the way? Well, here's some guidelines. First of all the perfect powers are simplified. So that means I don't want to see any cubed roots of 8 left in your problem because the cubed root of 8 is something we know to be 2. So that's one thing we can do. Make sure that all those perfect powers are taken care of. Second, all rational exponents are less than 1. So if I have x to the 5/2, that is something that can be simplified. I want that exponent to be less than 1, and we will work on that. Then, no radicals or rational exponents need to remain in the denominator. So, and here's what that would look like. Like 1 over the square root of x, or 1 over x to the 1/2. Those are equivalent. They mean the same thing. And we don't want either of those to happen because it's just improper at this level to leave radicals in the denominator. Once you get to calculus, it's a different story. But for right now and for pre-calculus, leaving a radical in the denominator is totally improper. And then I think there's one more. Scroll down. Yes, let's clear that ink though. All exponents under the radical are less than the index. So what that means, let's say I have a cubed root, x to the fourth, y squared, z to the fifth. Okay, so you're looking for, so here my index is 3. I'm going to inspect all of these exponents and make sure that none of them are higher than 3. Well, 4 is higher than 3, x to the fourth, and then z to the fifth is also higher than 3, so I would need to simplify the x to the fourth and the z to the fifth in order to be considered completely simplified. So here we have example 3, and we have to reduce the radical form of each expression. Now I'm looking inside. I can't simplify 7 over 16. There's no other x's to simplify. So I'm going to start off by rewriting the radical, the fifth root of 7, over the fifth root of 16 x cubed. Okay, and when you say that, and if I do that, you're like, no, Miss Honeycutt, you just put a radical in the denominator. Well, guess what? The radical was already there. I haven't changed what it meant, so I do need to get rid of the radical in the denominator. So I need to multiply by something that's going to cancel out the radical. And by the way, this is the fifth root. Now, I want to try to cancel out the fifth root, which means I need perfect fifth powers right here. So I need to multiply by something that's going to cause the denominator to have a perfect fifth power. Well, fifth root. Okay, so x cubed times x squared is going to be x to the fifth. So I'm going to multiply a numerator and a denominator by the fifth root of x squared. Let's see. So, well, let's just go ahead and see what that does. Okay, so in the top, that's going to give me the fifth root of 7x squared over the fifth root of 16x to the fifth. But x to the fifth is a perfect fifth power, so I can say that the fifth root of x to the fifth is just x. So really the denominator at this point, oh, I forgot where my eraser was, looks like this. X times the fifth root of 16. So now I need to think, okay, well, I've gotten rid of the radical for this part. I need to get rid of the radical for that part. Okay, is 16 a perfect fifth power? No. So I'm going to grab my power chart, and I'm going to see what is a perfect fifth power. And can I multiply 16 by something that will give me a perfect fifth power? Fifth powers are right here. So you can't multiply 16 to get 1. But I can multiply 16 by a number to get 32. 16 times 2 is 32. So now I'm going to multiply by the fifth root of 2 times the fifth root of 2, which will give me the fifth root. I can multiply what's inside. 7 times 2 is 14x squared. All over x times the fifth root of 32. But the fifth root of 32 is 2, so let's change that. And usually we write the x in the back, so 2x down here. And that should be done because now I don't have any radicals in my denominator. 14 is not a perfect fifth power, so I can't simplify there. This 2 exponent is smaller than the 5 index, so it's perfectly simplified. Here is one more like that. I split it up, have the cubed root 2n over the cubed root of 9m. So let's see, I'm trying to cancel out a perfect cube. So if I multiply, let's see, is 9 a perfect cube? No, but 27 is. And 9 times 3 is 27. So I'm going to multiply by the cubed root of 3, the numerator and the denominator. I also need to make m become m cubed so I can multiply by m squared. Now this time I'm doing it all in one step, so I don't have to do so many steps. All right, so now the numerator is going to look like the cubed root of 6 m squared n over the cubed root of 27 m cubed. So now my denominator is 3m. My numerator, cubed root 6m squared n. Now here's that product property again. We did take a single radical and break it up into multiple, but we can also work this the other way where we have multiple radicals and combine it into one if the indices are the same. So if those roots are the same. So this is an extra example, and it's going to help make the other part easier. Okay, so I have both fifth roots here. So I can go ahead and I can combine them into one. So this is the same as the fifth root of 16 times 8. So that would be the fifth root of 128. Now 128 is not a perfect fifth power, but 32 is. So 32 times 4. The fifth root of 32 is 2 times the fifth root of 4. Ta-da! Now here with B, you notice we've got two radicals that are not the same. They don't have the same indices, so I can't just go ahead and multiply what's inside. So we're going to have to try something else. Maybe I can split them up. So let's see. The fourth root of 27 times the fourth root of x squared times the square root of 3x. Okay, well, that doesn't seem to help very much. Okay, so then what if we split everything into fraction exponents? 27 to the 1/4, x to the 2/4, which is x to the 1/2, 3 to the 1/2, x to the 1/2. Well, right off the bat, I can see I can go ahead and combine the x to the 1/2 because they have the same base. I can add the exponents. Cool. So now I have 27 to the 1/4, 3 to the 1/2, and then x, if I add the exponents, 1/2 plus 1/2 is x to the first power. Now I can't combine 27 and 3 to the 1/2 because they don't have the same base. But I do know that 27 is the same as 3 cubed to the 1/4 times 3 to the 1/2 times x, and then I can multiply those exponents because it's a power of a power. So 3 to the 3/4 times 3 to the 1/2 times x. Now I can combine because they have the same base. So what is 3/4 plus 1/2? It is 5/4. So 3 to the 5/4 times x. And there we go.